Great.
Awesome. If there's any contract.
Awesome. All right. So hi everyone. Thanks for those who joining the webinars live, as well as those who will be watching this session later on YouTube. So this is Multimodal Weekly webinar session hosted by the 12 Labs. We've been meeting every Friday, Pacific time on a weekly basis over the past, I would say, 7 to 8 months. And here's some of the topics that we tend to cover on a weekly basis: news, research in multimodal AI and foundation models, innovative multimodal application in different verticals, specific videos and multimodal projects that you would like to share. And finally, sometimes we have internal team members give talks on using the 12 Labs platform and API. And for those of you who are not familiar with 12 Labs, we a startup building multimodal foundation models for video understanding. In some of the most recent week, we have a wide range of speakers, obviously researchers working at the intersection of video, vision transformer, vision language model. There was startup founder doing work on open source initiatives and fundamental for transformer architecture. And we also have like our team member who give talks about using our technology. So for this week, we have one talk given from the team at Huazhong University of Science and Technology. And you notice that, the time zone change here because, the team is always in China. So I have to accommodate, the webinar to let them be able to join. Professor Xinggang Wang and his PhD student Lianghui and Peng Liao will give a talk on their recent papers called Vision Mamba, efficient visual representation learning with bidirectional state space model. And so for those who doesn't know the context, this is a work that bring state of the art computer vision that leverage state space model, and Mamba is one of those transformer alternative that I think the community is very excited about, and it's very cool to see that architecture being leveraged for visual perception tasks. So I'm excited to hear how the authors will dive deeper into the motivation and present their work. So quick logistic on the session. Feel free to send your questions on Zoom chat. And we also have a short Q&A after the speaker finish. And since this is like a pretty small group, feel free to unmute yourself and ask questions in real time as well. With that, I stop sharing my screen and I let the speaker get started. So, I think any of you guys can start sharing your screen and go ahead with your presentation. That'd be great.
Okay, thank you very much, James. Thank you for inviting us to give this presentation to share our work. So, so Lianghui, please share the screen and introduce our Vim paper to us.
Yep, and also it'd be great if you guys can also like open the camera so people can see the speaker face.
Yeah.
Okay.
Hi, Lianghui.
Yeah.
Yeah.
Okay.
Yeah. So please turn on the camera and share your screen and give your talk.
Okay. Hi, James. Hi, everyone. I'm a doctoral student under Professor Xinggang Wang at Huazhong University of Science and Technology. It's a great honor to have the opportunity to be here today to share with you our latest work, Vision Mamba. You can directly access our GitHub project page via the QR code at the bottom right of the screen. Our paper is also available through the archive link. Now, let's start with the representation learning. Representation learning typically relies on 3 categories of backbones: CNN-based, transformer-based, and those based on RNN or SSM, such as Mamba. CNNs were initially widely applied to visual tasks, leveraging their spatial hierarchy to effectively extract local features from the input data. For example, images through convolutional layers. they can build a complex feature hierarchy across multiple convolutional layers. This spatial hierarchy makes CNNs very efficient in processing spatial data, such as images and videos. Additionally, the characteristic of parameter sharing allows the same weights to be applied to different locations, reducing the model's parameter count and enabling more efficient learning. Finally, the translational invariance enables CNN to recognize objects within images, regardless of their changing positions. This is because convolutional operations can capture local patterns which are consistent across different image locations. Next, we have the transformer architecture with its global attention. The transformer captures the relationship between any two positions in the input sequence through the self-attention, making it especially effective in handling long-distance dependencies. Unlike RNNs and CNNs, which process information through sequential hidden states or local neighborhoods, the transformer can perform a global analysis of the entire sequence. Its architecture is input dependent, generating different queries, keys, and values based on the input tokens. This grants it a flexible and robust feature processing capability. The transformer has been shown to excel in various tasks, including natural language processing, image recognition, and time series analysis, demonstrating its versatility and strong generalization ability across various representation learning tasks. For multimodal fusion tasks, it can also transform data from different modalities into sequences for unified processing. Lastly, we have Mamba, an integrated upgrade of the previous SSM architecture, like the S4. It shows strong long sequence modeling capabilities. It features a subquadratic architecture, which offers good efficiency. Finally, similar to the RNN-based and the SSM-based methods, it can effectively handle variable length sequences. Now we will introduce the state space model. The origins of the state space model can be traced back to the Kalman filter introduced in 1960. It can estimate the state of a linear dynamic system from observations containing noise and is widely used in the field such as signal processing. With the advancement of deep learning, the exploration of how to process sequential data led to the development of recurrent neural networks. RNNs can handle sequences of any length by parsing information through recurrent connections in the network, capturing information at different positions in a sequence. RNNs have shown significant potential in the fields like natural language processing and speech recognition. However, standard RNNs face challenges with gradient vanishing or exploding during training, making it difficult for the model to capture long-distance dependencies. To address these issues, long short-term memory networks were introduced in 1997, incorporating gating to adjust the retention and forgetting of information. This effectively solved the problems of vanishing gradients and long-distance dependencies, making LSTMs more effective for complex sequential tasks such as machine translation and speech recognition. And in 2014, the gated recurrent unit was proposed as an upgrade of LSTM aimed at simplifying its structure while maintaining performance. GRUs have shown similar performance to LSTMs on many tasks, but with fewer parameters and higher computational efficiency. S4, an improvement over the SSM-based method LSSL, optimizes the computation of convolutional kernels by moving the calculations to the frequency domain. This reduces the computational load and memory overhead previously associated with SSM computations. Last year, methods like RWKV and RedNight were introduced, incorporating the linear attention to build language backbones, achieving notable results in scaling up. Finally, the introduction of Mamba, which incorporates a data-dependent SSM, has shown impressive effectiveness and efficiency across various sequential processing tasks. Now, let's see the modern SSM. We will next introduce the prototype of modern state space models. For example, the word LSSL. Initially, such efforts were time invariant to ensure efficient computation. These models often adopt a recurrent form or utilize convolution kernels for parallel training. As illustrated in the figure and the equations, the process involves using matrix A to handle the hidden state at time t-1, then employing matrix B to process the input at time t, and finally using matrix C to manage the hidden state at time t to obtain the output for the current state. Okay. Now let's delve into the background of Mamba. As shown in the figure, Mamba proposes a GPU-efficient design. Generally, GPU storage is divided into high-speed SRAM storage and the conventional GPU HBM, with SRAM bandwidth being 10 times that of HBM. However, SRAM storage capacity is limited to approximately 20 MB. By concentrating computations on SRAM, Mamba significantly accelerates the processing speed. Moreover, conventional GPU computations often encounter scenarios where computation speed surpasses I/O speed. Mamba addresses this issue by minimizing the number of variables transfer rate, thus improving efficiency. During training, Mamba does not store a large number of intermediates for backward propagation. Instead, it opts to calculate these intermediate variables on the fly during the backward pass. Additionally, as shown in the bottom right corner of the diagram, Mamba's PPL perplexity results significantly surpass those of other linear attention networks and even slightly outperforms the highly optimized Transformer++ architecture. Okay, integrating an advanced architecture like Mamba into the vision domain naturally raises some questions. Let's consider these challenges. At first, how to make Mamba sensitive to the position of 2D images. Given that the Mamba architecture does not include positional encoding, it becomes challenging for 2D images patches to perceive their relative positions. A possible solution could involve incorporating explicit positional encodings within Mamba that allows it to learn or infer the spatial relationships between the different patches of an image. Secondly, how do we ensure global context modeling for Mamba? The causal paradigm of Mamba's architecture means that patches positioned earlier can struggle to be aware of those positioned later. Overcoming this challenge might require modifying the architecture to allow for non-causal processing that can effectively capture global dependencies across the entire image, regardless of the relative positions of the patches. Lastly, how to make Mamba promising for multimodal tasks. Beyond the meeting the demands of vision tasks, there's a desire for Mamba to be compatible with various modalities. This challenge could be addressed by designing Mamba to be modality agnostic, enabling it to process and integrate information from different sources, for example, text, audio, and images. This could involve creating a flexible input layer that can adapt to different types of data and developing a system that can convert different modalities into a unified representation before processing them through Mamba. Okay, then we will introduce our Vision Mamba. Vision Mamba features an architecture designed to enhance spatial awareness and global context understanding in image processing tasks. The structure incorporates patch embeddings with added position embeddings, facilitating spatial information perception. The block design introduces backward COM1D and backward SSM, enabling the model to perceive image sequences from different directions and thus capture a comprehensive global context. Furthermore, WIM's architecture allows for the activation or deactivation of backward SSM, making it adept at handling tasks requiring a global understanding of images, as well as the causal modeling of 1D sequences. This flexibility positions WIM as a versatile tool for a wide range of image and sequence modeling applications. In a comparative architecture diagram between WIM and VIT, the overall structure appears similar, with the key differences being the use of Vision Mamba blocks in WIM as opposed to transformer blocks in VIT. Additionally, there's a distinct approach to the placement of the class token. While in self-attention, all token positions are computational equivalent. This is not the case with SSM. Various placements for the class token were tested in WIM, and positioning it in the middle was determined to achieve the best performance. WIM's efficiency analysis highlights its strengths across several dimensions. The first, I/O efficiency. WIM reduces I/O by using recomputation for on-the-fly calculation in the thread. And the memory efficiency. It doesn't store intermediates, opting to recompute them during the backward pass instead. And last, the computation efficiency. SSM has lower computation complexity compared to the self-attention. And the results for image classification demonstrate WIM's efficiency. Comparative charts show that at a resolution of 1248, WIM is 2.8 times faster than DATE and consumes 86.8% less GPU memory. Vision Mamba supports key models across different architectures: CN-based ResNet, transformer-based VIT and DEIT, and SSM-based S4ND, demonstrating its superior efficiency and effectiveness in image processing tasks. Okay, Vision Mamba also Vision Mamba demonstrates superior performance not only in image classification but also in downstream dense prediction tasks. Utilized as a backbone network, WIM-based ARPANET outperforms the DATE-based ARPANET on the ADE dataset, indicating its better capability in handling complex semantic segmentation tasks. Furthermore, on the COCO dataset, WIM surpasses DATE in both object detection and instance segmentation tasks, showcasing its versatility and effectiveness across various vision tasks. In designing the WIM architecture, various bidirectional strategies were tried with. assessing their impact on ImageNet classification and ADE segmentation results. At first, the bidirectional layers, setting different layers to forward and backward directions improves the dense segmentation outcomes, but slightly reduce the classification accuracy. Then the bidirectional SSM. Implementing bidirectional SSM for each layer enhanced the segmentation results beyond the baseline, but classification suffered marginally. Bidirectional SSM and causal convolution. Setting both SSM and causal convolution to bidirectional not only improved the segmentation results, but also enhanced the classification performance. Additionally, the positioning of the class token was evaluated due to the non-equivalence of token positions in the Vim architecture. Various strategies were tested, including min pooling and max pooling, placing the class token as the sequence's head, tail, or both, and positioning it in the middle. Finally, placing the class token in the middle achieves the best performance. Okay, for the further applications of Vim, we want to talk about the multimodal pre-training first. Vim, sharing Mamba's architecture, enables multimodal pre-training using a causal with prefix paradigm and only activates backward SSM for image patches, enhancing its capability for complex multimodal tasks. Yeah. And other application could be the image generation. DIS adopts Vim as its foundational architecture for diffusion models, treating all elements, timestamp, condition, and image patches as tokens. By utilizing bidirectional Vim, DIS achieves global context understanding, enhancing the model's performance in generating images. DIS also outperforms previous diffusion-based methods and demonstrates promising scaling capabilities, indicating significant advancement in image generation tasks. And diffuse SSM also use similar method in the image generation domain. Diffuse SSM employs a gated bidirectional SSM block to replace the vision transformer block in DIT, enhancing its capability for handling complex dependencies in data, and it is good at dealing with images with large resolutions. Diffuse SSM has lower G-flops when compared with DIT. And diffuse SSM outperforms previous diffusion-based techniques and demonstrates notable scaling potential, indicating its effectiveness for generation tasks. The further application also include video generation or video recognition. As a fundamental component of Sora, DIT also faces challenges in modeling long temporal spatial sequences. Vim, with its superior memory, I/O, and computation efficiency in handling long sequences, emerges as a promising foundation for enhancing video task performance for both generation and recognition. Okay, thanks for listening. Thanks for listening. Is there some questions?
Hi, James. Our sharing. Oh, Brian.
Okay. I find that James was offline. Okay. We can wait a minute.
Yeah. I find there's a question about diffusion SSM. Maybe Lianghui and Benson can reply to the question. And if anyone has a question, you can write, or you can open your microphone and directly talk to us. Lianghui, you may repeat the question in the chat window.
Okay, let me see.
Yeah, so there was a question, I think, asking about Vision Mamba and then Mamba. I think that was a while back.
Oh yeah. That's a good question. Since Mamba is a concurrent work of our purpose region, and the main difference lies in the Mamba features using the Mamba in 2D image layout, and with its proposed 2D selective scans modules, and it used the swing micro architecture, while our proposed rings directly inherit from vision transformer and treats image as a 1D sequence without introducing 2D inductive bias, and making our rings can be more compatible with multimodality input and other applications.
Yeah, I may give a high-level answer to this question. So Mamba can be seen as the swing transformer, and when comparing Mamba with transformer, Mamba is the swing transformer because it has 2D priors and window attention, and while our Vision Mamba is a plan transformer. We do not have any 2D inductive bias, and why plan VIT is important? You may find that in both Sora and ChatGPT, they all use plan transformer. So we focus on developing the sequence-to-sequence learning style based on Mamba. Very sorry, because I have to take care of my kids. Sorry.
No worries. No worries. I think that's I can answer the question. Yeah, swing transformer and plan transformer. I think that's the main thing that I got from that answer. Yeah. Is there any other question from the audience? Either you can unmute yourself, or you can just put in the chat for Lianghui to tackle. Yeah, so maybe I have a question myself. Can you go back to the slide when you say multimodal pre-training?
Okay.
Yeah, so here you said multimodal beam can use the pre-training paradigm of causal with prefix. Can you explain more? Like, what does it mean? What is causal with prefix means in this context?
Okay, you can see the attention mask shown in this figure. For the left one, it is a fully visible attention mask. The X1 could see the X5, the X5 can see X1. But for the causal version, the X1 cannot see the X5, and the X5 can see all the tokens before it. And for the causal with prefix, which means that for some tokens, they share the fully visible, and for the next one, they are the causal version. This will lead to a global sharing for some tokens, as mentioned in T5, which is a promising paradigm for the multimodality pre-training. different from the Calypse paradigm, we think that the interleaved pretrain using Mamba with such a causal with prefix paradigm can be more promising. Yeah.
I see. Yeah. So contrasting with like interleave text to image gene clip, you think this one is a better pre-training paradigm, right, for multimodal purpose.
Yeah.
So there's a question here on the chat. Can Vision Mamba be extended for 3D generation?
Yeah.
Yeah, there is a follow-up work named Point Mamba. They follow the Vision Mamba paradigm to process point cloud representation. So it's natural to use our Vision Mambas to generate the 3D point cloud like the point Mamba. So the Vision Mamba is very possible to be extended for the 3D generation.
Okay, I see the James icon is freeze again.
Hey, you guys. Sorry, I got kicked out of my own meeting. It was some Wi-Fi issue at the office. Sorry about that. Did I miss anything important?
No.
Yeah.
Yeah.
Yeah, I saw here people link to the chat. Point Mamba, right?
Yes,
Oh,
yes.
Point Mamba. Got it. So there's another question right here. You mentioned about Mamba being useful in multimodal tasks. So can it be used for any-to-any generation?
Yeah, we think it is promising to achieve that because the Mamba could have a more versatile system that could take in different modalities input, and then it can also use a detokenizer to translate the hidden state to any format of output. So I think the any-to-any paradigm for Vision Mamba is also promising. Yeah.
Yeah, I hope that's so. Saha, I hope that answers your question. Yeah, if you put more question in the chat, I think there's a lot of good question right here around the capabilities of the model. Can you go back to the slide on image generation? So I think you mentioned DIS and diffuse SSM, right?
Yeah.
I see. So when you say like using Vim as a basic architecture for diffusion model, can you extrapolate on that? Like where in this diagram? Yeah, just walk through this slide one more time so I can get the idea. Like where do you use SSM in diffusion model?
Lianghui, James recommend you go through this slide in second time.
Okay. This is the displacement of the DIS. DIS is a diffusion network, it replaced the backbone, the basic block of DIT to our Vim block, and it treats all elements such as the timestamp, the condition, and the image patches, all as tokens. You can say this is the timestamp and this is the condition, and
I see.
these are the image patches. Okay, and the DIS achieves the global contextual understanding through the Vim block, which enhances its performance in generating images. And we can see the result here. DIS outperforms other diffusion-based methods and the transformer-based methods here. The UNet-based, the transformer-based, and the GAN-based generation method. And it also shows great scaling ability from the small size to the H size. Okay, for another one, the diffuse SSM, which uses a gated bidirectional SSM block to replace VIT block in DIT. Just a little thing as the DIS, but the bidirectional SSM here is is not input dependent. It's just a conventional bidirectional SSM, yeah. But it also achieves great ability in the scaling. Yeah. And diffuse SSM also outperforms previous diffusion-based techniques and demonstrates notable scaling ability here, and indicating its effectiveness here.
I see. Yeah. Thanks for sharing that. DIT stand for diffusion transformer. Is that correct?
Yeah.
Got it. So as you already in this slide, can you go to the next slide as well on video generation, video recognition?
Okay. Do you mean this page?
Yeah, I think this is like super relevant for labs and for us because we work in the video space. So so I see the argument here is diffusion transformer struggle with long temporal spatial sequence modeling, and you think that replacing that with the backbone Vim architecture could solve that problem, right?
Yes. Because we have seen that in the application users, the storers and their token length may reach million scale. So in that case, the subquadratic complexity of transformer will make it hard for the low tops device. So the proposed Mamba may be the efficient substitute of Sora. Yes.
I see. So it sounds like it's going to be useful for both the recognition part and the generation part, right?
Yes.
Very nice. Very cool. Yeah, so I'm curious, has there any academic research that try to apply Mamba or any other like state space model in the video domain that you are aware of?
No, not yet. But you can stay tuned for work from our group. We may work on that.
Nice. Very cool. Yeah, I don't think I have another question. I think that's all from my end. The audience, do you guys have any question for the speakers? If so, please just put in the chat or unmute yourself. I'm just curious about so you're in the same computer vision lab in Huazhong University, right, in China?
Yeah.
Can you, maybe either you or Professor Xinhuang, can you tell more a bit about kind of the focus of your research lab, and what are some of the notable other projects besides Vision Mamba that you are working on?
We are also trying to apply Vision Mamba to some other vision tasks that facing the long sequences bottleneck, such as video recognition, video generation, or the yeah. Our lab aims for the vision perception tasks such as object detection and semantic segmentation. And we now our lab also works on the large language models and some advanced foundation models such as Mamba. Yeah.
So yeah, it's a combination of like transformer architecture and foundation models. Yeah, looks like they sent a question here in the chat. Is there any possible future research work with diffusion using Mamba, since there already works like diffuse SSM and DIS, which are doing better than DIT?
Yeah, that's a great question. For the DIS and diffuse SSM, their results table both shows competitive results, and I think comparing with DIT, the diffusion model with Mamba can have some efficiency in FPS and the GPU memory usage.
And for the extended scenario like video generation, we think Mamba may be the top player in that game.
Yeah. Yeah, so I hope that answers the question. Great.
Sorry for that.
Yeah, no worries. Yeah, thanks for the answer. Good. Actually, I have another question around state space model and transformer alternatives. So Mamba is probably the most famous state space model, but as far as I'm aware, there's also like a couple other options, right? Like Stripe Hyena is one that I heard of. There's also retention net, right? RedNet, and there's one called linear transformer that I heard recently. What else? Yeah, so I'm kind of curious. Do you also see these other variants of state space model be effective, right? To apply, for some of these use cases around image generation, video generation, etc.
Okay. We think the Mamba is also a kind of method with the linear attention. Actually, the linear attention methods are can be regarded as the modern RNN, and they share the similar architecture.
Okay.
We can find that the A could be regarded as the forgetting gate. B is used to process the current input, and C are used as the projection to the final output YT. And they all will keep a hidden states during the training or inference. Yeah, and a surprising thing for us is that we can find the Mamba's result can slightly outperform the transformer plus. It's a great news because, as we all know, at the past few years, we do not use the linear attention network because their performance is a little bit worse than the full attention transformer. But now Mamba shows that the RN-like models can also share the similar performance with the full attention transformers, but with great efficiency. Yeah.
Yeah. No, thanks for sharing that. This is pretty interesting to me because we actually have the author of RWKV and linear transformer in this webinar before. So I think I'm like very interested in, all the alternative to transformer, and yeah, I think what you show here is kind of display that very, very well.
Okay. I also think RWKV is a promising architecture because it can scale up to a very large size. I think all the modern linear attention architecture, if we want to use it, there must be someone to prove that it could be scaling up to a extreme large size, like transformers size. Yeah.
Yep. Perfect. Yeah, I think that's everything I have on my end. So unless there's no other question from the audience, I think we can, conclude our webinar just, a couple minutes earlier. Thanks, Lianghui for walking over the presentation, talk about Vision Mamba, and answer like very technical question from the audience. And yeah, thanks for Professor Singang as well for contributing some of your perspective. Yeah, the recording of this session will be available probably in 2 weeks-ish when it's on YouTube. I'll be sure to put it on a Discord and share it with the author as well so they can promote it on the channel. And thanks everyone for joining us again. We run Multimodal Weekly every Friday, typically around 1:30, but due to some speaker time zone, I have to adjust it for a few sessions. So don't be surprised if you see like any change in the webinar time for the future upcoming session, especially for speaker from Asia or Europe. Yeah, with that, appreciate everyone for joining, and enjoy the rest of your weekend. Bye-bye.
Bye-bye. Thanks for having us.
Yeah.
Thanks,
Of
everyone.
course, yeah.
Thanks
Lianghui,
for
if you can stop screen sharing, that'd be great.
Okay.
Awesome.